20,000 years ago, deep in caves where firelight danced against stone walls, our ancestors did something extraordinary. They looked up at the night sky, saw 7 stars clustered together like jewels scattered on black velvet, and felt compelled to recreate that pattern on the cave wall. The Pleiades star cluster, what we now know as the 7 Sisters, became humanity's first recorded question about the cosmos. Not a practical marking of seasons or navigation, but pure wonder, captured in ochre and charcoal. Here was the birth of astronomy. Humans recognizing patterns in the heavens and feeling an irresistible urge to understand them. The universe had spent 13.8 billion years arranging matter into increasingly complex patterns. Stars formed and died, heavy elements scattered across space, planets coalesced from cosmic dust. Then, in what amounts to the last few seconds of cosmic time, matter achieved something unprecedented. Time. It became curious about itself. Through us, the cosmos developed eyes to see and minds to wonder. But that cave painting was just the beginning. The questions our ancestors asked in flickering firelight would eventually lead to revelations so profound they would reshape our understanding of existence itself. Fast forward to ancient Babylon, around 600 years before the Common Era. Here's what's really happening in this cradle of civilization. Scribes are creating the world's first systematic astronomical records, tracking the movements of celestial bodies with obsessive precision. They observe Venus, that brilliant morning and evening star, for 64 years straight, recording its every appearance and disappearance. Night after night, generation after generation, they document the planet's dance across the sky. These weren't just idle observations. The Babylonians discovered something remarkable. The heavens moved in patterns, precise, predictable, mathematical patterns. Venus appeared in the same positions relative to the stars in cycles lasting exactly 584 days. They mapped the zodiac, divided the circle into 360 degrees, and created the foundations of mathematical astronomy that we still use today. The universe has a surprise for us here. These ancient astronomers, working without telescopes or computers, achieved accuracy that staggers the modern mind. They predicted planetary positions centuries in advance. They calculated the length of a year to within 26 minutes of our modern measurement. How? Through the power of patient observation and the mathematical language hidden in celestial motions. Meanwhile, in Egypt, an even more spectacular demonstration of cosmic awareness was taking shape. The Great Pyramid of Giza, completed around 2,560 years before the Common Era, stands as humanity's first monument to precision astronomy. Here's what's actually happening with this architectural marvel. The pyramid's base is level to within just 2.1 centimeters across its 230-meter width. The structure is aligned to true north with an accuracy of 3/60ths of a degree, more precise than the Greenwich Observatory built 4,000 years later. But the real revelation lies in the pyramid's internal chambers. The so-called King's Chamber contains shafts that point directly to specific stars. Orion and Draco in the northern shaft, Sirius and Orion's belt in the southern. These weren't decorative choices. The ancient Egyptians believed their pharaohs would join Orion in the afterlife, and they built star maps in stone to guide the journey. The precision is breathtaking. When you consider that these builders worked without steel tools, without wheeled vehicles, without even pulleys, their achievement becomes almost incomprehensible. Yet they understood something profound about their relationship to the cosmos. They saw themselves not as separate from the heavens, but as participants in a cosmic order that connected the smallest human actions to the grandest celestial cycles. This pattern of wonder and precision emerges across cultures. In the Americas, the Maya were developing astronomical knowledge that rivals our modern understanding. Between 300 and 900 of the Common Era, Mayan astronomers were tracking Venus with such accuracy they could predict its position 8 years in advance to within 2 hours. They calculated the lunar month to within 7 seconds of our modern measurement. They created calendars so sophisticated they accounted for the slight irregularities in Earth's orbit around the Sunday. The Maya discovered that Venus, Earth, and the Sun align in the same configuration every 8 years. They found patterns within patterns, cycles within cycles, all recorded in stone tablets and intricate astronomical tables. At Chichen Itza, they built the Caracol Observatory with windows precisely aligned to track Venus at its extreme positions. During spring and autumn equinoxes, the shadows on the Great Pyramid create the illusion of a serpent descending the steps, cosmic clockwork made visible. Here's what makes these achievements so remarkable. These civilizations understood that the cosmos operates according to mathematical laws. They discovered that beneath the apparent chaos of celestial motions lies profound order. The same gravitational forces that keep planets in their orbits, the same physics that governs the nuclear furnaces inside stars, were revealed through patient observation and mathematical insight thousands of years before we understood the underlying mechanisms. But the real revolution was still coming. January 7th, 1610. Galileo Galilei, working in Padua, points his homemade telescope toward Jupiter. What he sees through that crude instrument, barely more powerful than a pair of modern binoculars, shatters humanity's understanding of the cosmos. 4 tiny points of light dance around Jupiter like moons around a planet. But this is impossible according to the accepted wisdom of the time. Everything in the heavens is supposed to orbit Earth. The sun, the moon, the planets, the stars, all of creation revolves around our terrestrial home. Yet here are 4 celestial bodies clearly orbiting something else entirely. Night after night, Galileo tracks these moons, Io, Europa, Ganymede, and Callisto, though he calls them the Medicean stars in honor of his patrons. He watches them appear and disappear as they pass behind Jupiter, their movements following precise mathematical patterns. The implications are staggering. If moons can orbit Jupiter, then perhaps Earth isn't the center of everything. Perhaps Copernicus was right when he suggested that Earth orbits the Sunday. The universe suddenly becomes vast in ways that terrify and exhilarate. We exist not at the center of creation, but on one world among many, orbiting an ordinary star in an apparently endless cosmos. The psychological impact cannot be overstated. Humans had to reimagine their place in existence itself, but Galileo's telescope reveals even more unsettling truths. The moon, that perfect celestial sphere, shows a surface scarred with craters and mountains. Venus displays phases like our moon, growing fuller and thinner as it orbits the Sunday. The Milky Way resolves into countless individual stars, suggesting that the cosmos contains far more than anyone had imagined. Here's what's really happening in these pivotal moments. Humanity is discovering that the universe operates according to physical laws that can be understood through observation and mathematics. The same forces that govern falling apples also keep planets in their orbits. The same principles that explain the motion of Jupiter's moons apply throughout the cosmos. This realization sets the stage for 3 centuries of revolutionary discoveries. Newton will soon decode the mathematics of gravity, showing how a single law explains both terrestrial motion and planetary orbits. The cosmos transforms from a mysterious realm, governed by divine whim, into a vast machine operating according to comprehensible principles. But the greatest revelations are yet to come. Fast forward to 1905, Albert Einstein, working as a patent clerk in Bern, publishes a paper that begins with a thought experiment so simple a child could understand it, yet so profound it reshapes our understanding of reality itself. Einstein imagines riding alongside a beam of light, traveling at light speed through space. What would you see? What would the universe look like from the perspective of a photon? The answer leads to special relativity and the stunning realization that space and time are not separate, absolute entities, but aspects of a single, flexible fabric called space-time. Time passes differently for objects moving at different speeds. Space contracts and expands depending on your frame of reference. The universe becomes far stranger than anyone had imagined. But Einstein isn't finished. In 1915, he publishes General Relativity, revealing that gravity isn't a force pulling objects together, but the curvature of space-time itself. Imagine a bowling ball placed on a stretched rubber sheet. The ball creates a depression that causes marbles to roll toward it. Massive objects like stars and planets warp the fabric of space-time in the same way, creating what we experience as gravitational attraction. This isn't just elegant mathematics. It's a complete revolution in how we understand reality. Space can be bent, stretched, even torn. Time can slow down or speed up. The universe becomes a dynamic, evolving entity rather than a static stage where events unfold. Then comes 1929 and Edwin Hubble's earth-shaking discovery. Using the 100-inch telescope at Mount Wilson Observatory, Hubble measures the light from distant galaxies and finds something impossible. The galaxies are moving away from us, all of them, in every direction, and the farther away they are, the faster they're receding. The implications hit like a thunderbolt. If every galaxy is racing away from every other galaxy, then the universe itself must be expanding. Not expanding into something, expanding as a whole, with space itself stretching between galaxies like dots drawn on an inflating balloon. This discovery leads to the most profound question humanity has ever asked. If the universe is expanding now, what was it like in the past? Run the expansion backward in time, and every galaxy, every star, every atom in existence converges to a single point. The entire observable universe, everything we can see to the very edge of space, once compressed into a volume smaller than the period at the end of this sentence. The Big Bang Theory emerges from this realization, describing how the cosmos began in a state of unimaginable density and temperature, then expanded and cooled to create everything we see today. Time itself began with this expansion. Before the Big Bang, before has no meaning, like asking what lies north of the North Pole. But here's where the story becomes even more extraordinary. Each answer births new questions in endless succession. If the universe began with the Big Bang, what caused it? If space can expand, what lies beyond the observable universe? If matter and energy came from nothing, what fundamental principles govern this creation? By the early 20th century, humanity has transformed from creatures huddled around cave fires, painting star patterns on stone walls, into beings capable of questioning the very nature of existence. We've discovered that we live in an expanding universe filled with billions of galaxies, each containing billions of stars. We've learned that matter and energy are interchangeable, that space and time form a unified fabric, that the cosmos operates according to mathematical laws we can comprehend. Yet for every mystery we solve, the universe reveals new depths of strangeness. The atoms in our bodies were forged in the nuclear furnaces of dying stars. The calcium in our bones, the iron in our blood, the oxygen in our lungs are found. All of it created when ancient stars exhausted their fuel and exploded, scattering heavy elements across space. We are made of stardust, not poetically but literally. The light reaching our eyes from distant stars began its journey years, decades, even centuries ago. When we look at the night sky, we're seeing the universe as it was, not as it is. We're time travelers, observing the past through the simple act of looking up. And we've only just begun to understand how strange existence really is. The ancient cave painters who first wondered about the Pleiades could never have imagined where their questions would lead. From those first tentative marks on stone walls to Einstein's equations describing the curvature of space-time, humanity has embarked on the greatest adventure in history, the quest to understand our place in an infinite cosmos. But as we'll discover in the chapters ahead, the visible universe, all the stars and galaxies we can see, represents less than 5% of everything that exists. We swim in an invisible ocean of dark matter and dark energy, mysterious substances that outweigh and outpower everything we can observe. The cosmos hides secrets that challenge our most fundamental assumptions about reality. The journey that began with wonder 20,000 years ago has led us to the edge of the incomprehensible, and the most mind-bending discoveries still lie ahead. In 1933, a Swiss astronomer named Fritz Zwicky made an observation that would haunt physics for the next 90 years. Studying the Coma galaxy cluster through the massive telescope at Mount Wilson Observatory, Zwicky measured how fast individual galaxies were moving within this cosmic neighborhood. What he found defied everything astronomers thought they knew about gravity and matter. The galaxies were moving impossibly fast, so fast they should have scattered like sparks from a struck flint, flying apart and disappearing into the vast darkness between galaxy clusters. Yet there they were, bound together in a gravitational dance, orbiting their common center of mass in perfect harmony. Something was holding them together with invisible chains. Zwicky calculated the mass needed to generate enough gravity to keep these speeding galaxies bound. The answer staggered him. The cluster needed to be 5 times more massive than all the visible stars and gas combined. 5 times more matter than anything telescopes could detect. He called this missing mass dunkel materie, dark matter. Here's what's really happening in the Coma cluster. We're seeing the first evidence that the universe is not what it appears to be. The stars, planets, and gas clouds that telescopes reveal, everything that shines or glows or reflects light, represent only a tiny fraction of what actually exists. We live in a cosmos where the vast majority of matter remains completely invisible. For 40 years, Zwicky's discovery remained a curious anomaly, a puzzle for theorists to debate in academic journals. Most astronomers assumed the missing matter would eventually be found, perhaps in dim stars too faint to detect, or in clouds of cold gas floating between galaxies. The universe couldn't really be hiding 5/6 of its contents from view. Then came Vera Rubin. In the 1970s, working at the Carnegie Institution, Rubin began a systematic study of spiral galaxies, measuring how fast stars orbit their galactic centers. According to Newton's laws of gravity, stars at the edges of galaxies should move more slowly than those near the center, just as the outer planets in our solar system orbit more slowly than the inner ones. Mars takes nearly 2 years to complete an orbit, while Mercury races around the Sun in just 88 days. But when Rubin measured the rotation speeds of spiral galaxies, she discovered something impossible. Stars at the very edges of these cosmic pinwheels were moving at the same speed as those closer to the center, roughly 220 kilometers per second. At these velocities, the outer stars should have been flung into intergalactic space billions of years ago, like mud flying off a spinning bicycle wheel. Yet galaxy after galaxy showed the same pattern. Spiral arms maintained their elegant structure over billions of years, stars held in perfect formation by some invisible gravitational influence. Rubin had discovered that individual galaxies, like galaxy clusters, were dominated by matter that telescopes couldn't see. The implications were staggering. If galaxies needed dark matter to hold themselves together, and galaxy clusters needed dark matter to remain bound, then dark matter wasn't some exotic rarity. It was the dominant component of the universe itself. Everything we could see and touch and study represented less than 20% of the cosmic inventory. But what is dark matter? Here's where the mystery deepens into something almost science fictional. Dark matter doesn't emit light, doesn't absorb light, doesn't interact electromagnetically in any way we can detect. It makes its presence known only through gravity, bending space and time around itself like Einstein's bowling ball on a rubber sheet, but remaining otherwise invisible to every instrument we've devised. The hunt for dark matter has driven scientists to extraordinary lengths. Deep beneath the Black Hills of South Dakota, in the former Homestake gold mine, researchers have built one of the most sensitive detectors ever conceived. The large underground xenon experiment sits a mile below ground, shielded by solid rock from the cosmic rays that constantly bombard Earth's surface. Here's what's actually happening in this underground laboratory. Scientists have filled a tank with 370 kilograms of ultra-pure liquid xenon, cooled to -100 degrees Celsius. The xenon acts like a cosmic burglar alarm, designed to register the incredibly rare occasions when a dark matter particle might collide with an atomic nucleus. The numbers involved are mind-bending. According to current theories, billions of dark matter particles stream through every square centimeter of your body every second. They pass through Earth as if our planet were made of empty space, traveling unimpeded through thousands of kilometers of solid rock and metal. Right now, as you listen to these words, an invisible rain of dark matter particles is falling through your brain, your heart, your bones, completely undetected by your senses. The xenon detector represents humanity's attempt to catch these ghostly particles in the act. When a dark matter particle occasionally strikes a xenon nucleus, FS, perhaps once in several months of continuous operation, FS, it should produce a tiny flash of light and a small electrical signal. Scientists watch for these rare events with the patience of astronomers waiting for eclipses. Similar experiments operate around the world, in abandoned mines in Italy, in underground laboratories in Japan, in particle accelerators that slam protons together at nearly the speed of light, trying to create dark matter particles in controlled collisions. The global effort to detect dark matter directly has cost billions of dollars and engaged thousands of the world's most brilliant physicists. Yet after decades of searching, dark matter remains stubbornly invisible. Every experiment designed to detect it has failed. The particles, if they exist, interact so weakly with ordinary matter that they might as well inhabit a parallel universe that shares our space but remains forever beyond our reach. Some scientists have begun to wonder whether dark matter exists at all. Perhaps our understanding of gravity is incomplete. Perhaps Newton's and Einstein's equations need modification on cosmic scales. Alternative theories like modified Newtonian dynamics suggest that gravity behaves differently over vast distances, eliminating the need for invisible matter. But the evidence for dark matter extends far beyond galaxy rotation curves. The cosmic microwave background, i.e., the afterglow of the Big Bang still visible today, shows tiny temperature fluctuations that match computer simulations only if the universe contains exactly the right amount of dark matter. Gravitational lensing, where massive objects bend light from more distant sources, reveals dark matter's presence through the way it warps space around galaxy clusters. The most compelling evidence comes from the Bullet Cluster, two galaxy clusters that collided 5 billion years ago. When the clusters smashed together, their gas clouds slammed into each other and heated up, glowing brilliantly in X-ray wavelengths. But gravitational lensing shows that most of the mass in each cluster passed right through the collision, unaffected by the cosmic crash. The visible matter crashed and burned. The dark matter sailed through unperturbed. This invisible ocean that surrounds us represents 85% of all matter in the universe. Dark matter provided the gravitational scaffolding on which galaxies formed. Without it, the universe would be a sparse collection of isolated stars, wandering through empty space, never gathering into the rich galactic structures we see today. Yet dark matter is only part of the cosmic mystery. In 1998, two independent teams of astronomers embarked on an ambitious project to measure how fast the universe's expansion was slowing down. Using Type Ia supernovae, exploding white dwarf stars that shine with predictable brightness, as cosmic standard candles, they planned to trace the universe's expansion history across billions of years. Logic seemed straightforward. Gravity pulls everything together. So the universe's expansion should be decelerating since the Big Bang, gradually slowing as galaxies tug on each other across cosmic distances. By measuring supernovae at different distances, and therefore different ages, astronomers could determine exactly how much the expansion had decelerated over cosmic time. The teams worked independently, analyzing data from dozens of distant supernovae, checking and rechecking their calculations. When they compared results, both groups had reached the same impossible conclusion. The universe wasn't slowing down. It was speeding up. The expansion of space itself was accelerating, as if some mysterious force was pushing galaxies apart with ever-increasing strength. The discovery was so unexpected, so contrary to theoretical predictions, that both teams spent months trying to find errors in their analysis. But the data was unambiguous. Something was driving cosmic acceleration on the largest scales imaginable. Scientists named this mysterious influence dark energy, though the term reveals more about our ignorance than our understanding. Dark energy appears to be a property of space itself, causing empty space to stretch and expand. As the universe grows larger, more space comes into existence, and with it, more dark energy. The acceleration feeds on itself, growing stronger as time passes. Here's what makes dark energy truly mind-bending. It represents approximately 68% of all energy in the universe. Combined with dark matter's 85% of all matter, we arrive at a stunning realization. Everything we can see and study, every star, planet, galaxy, and nebula, comprises less than 5% of existence. We are the cosmic equivalent of foam on the surface of a vast, dark ocean. The universe consists of roughly 68% dark energy, 27% dark matter, and 5% ordinary matter. We exist as a tiny minority in a cosmos dominated by phenomena we cannot see, cannot touch, and barely comprehend. It's as if we've been studying the whitecaps on ocean waves, while remaining oblivious to the depths beneath. Dark energy's effects become more dramatic as time passes. Currently, space expands slowly enough that gravity can still hold galaxies and galaxy clusters together. But as cosmic acceleration continues, even these gravitational bonds will eventually break. In approximately 100 billion years, distant galaxies will be receding so fast that their light will never reach us. Future astronomers in the Milky Way will see only our local group of galaxies in an otherwise empty sky. The far future becomes even stranger. In perhaps 1 trillion years, dark energy will overcome gravity on all scales. Galaxy clusters will dissolve, then individual galaxies, then star systems, and finally atoms themselves might be torn apart in a cataclysm called the Big Rip. Space will expand so rapidly that no force in nature can hold matter together against the cosmic acceleration. Yet, for all our sophisticated theories and mathematical models, we have no idea what dark energy actually is. The most obvious candidate, the quantum energy of empty space itself, predicts an acceleration 120 orders of magnitude stronger than what we observe. It's the worst prediction in the history of physics, missing the mark by more than the number of atoms in the observable universe. Alternative theories abound. Perhaps dark energy is a new type of field, like an electric or magnetic field that permeates space and drives acceleration. Perhaps our understanding of gravity needs fundamental revision on cosmic scales. Perhaps we live in a higher dimensional space where gravity leaks into unseen dimensions, weakening its pull over vast distances. Some theories suggest dark energy might not be constant. It could strengthen or weaken over time, or even reverse direction, eventually causing the universe to contract instead of expand. Others propose that dark energy is an illusion created by our position in an unusually empty region of space, making distant galaxies appear to accelerate when they're actually maintaining constant speeds. The search for answers drives cutting-edge research around the world. The Dark Energy Survey maps hundreds of millions of galaxies to trace cosmic acceleration across billions of years. The upcoming Roman Space Telescope will measure the expansion history with unprecedented precision. Underground experiments seek not only dark matter particles but also the hypothetical particles that might comprise dark energy. Meanwhile, we exist as conscious beings made of ordinary matter, floating in an invisible ocean we can barely perceive. Every breath you take, every heartbeat, every thought passing through your mind represents a profound rarity, nay, ordinary matter organized into patterns complex enough to contemplate their own existence in a universe dominated by mystery. The dark matter streaming through your body right now connects you to the cosmic web, the vast network of invisible scaffolding that shapes the largest structures in the universe. The dark energy stretching space around you drives the very expansion that will determine the cosmos's ultimate fate. We swim in an ocean of the unknown, yet somehow, through patient observation and mathematical insight, we've begun to map its invisible currents. This is perhaps the most humbling discovery in the history of science. We are not merely small in a vast universe. We are made of the minority component in a cosmos dominated by phenomena that remain almost entirely mysterious. Yet our minority status hasn't prevented us from detecting these invisible influences and beginning to understand their cosmic significance. The next chapter in our journey takes us even deeper into mystery, to the very beginning of time itself, where the known laws of physics break down and reality becomes stranger than any science fiction. 13.8 billion years ago, everything you've ever seen or touched or imagined, every galaxy, every star, every planet, every atom in your body, was compressed into a point smaller than a proton. The temperature reached 10 to the 32nd degrees Celsius, a heat so intense that the fundamental forces of nature themselves broke down and merged into a single, unified force. This was the beginning, the moment when time itself started ticking. But here's where our story ventures into territory so strange that language itself begins to fail us. When we ask what happened before the Big Bang, we're asking what occurred before time existed. It's like asking what lies north of the North Pole, or what color Thursday smells like. The question seems to make sense until you examine it closely. Yet modern physics has developed tools to probe even these seemingly impossible questions, and the answers suggest that our universe might be far stranger and far vaster than anyone ever imagined. Let's start with what we know about those first incomprehensible moments. In the beginning, the universe existed in a state called the Planck epoch, lasting from time 0 to 10 to the negative 43 seconds after the Big Bang. During this infinitesimal instant, space and time themselves fluctuated like waves on an ocean, appearing and disappearing in quantum foam at scales billions of times smaller than a proton. Here's what's actually happening at these impossible scales. The very notion of smooth, continuous space-time breaks down. Space becomes granular, pixelated like a computer screen viewed under extreme magnification. Time doesn't flow smoothly but stutters in discrete jumps. The familiar laws of physics dissolve into quantum uncertainty, where cause and effect lose their meaning and particles pop into existence from pure nothingness. But quantum mechanics reveals something extraordinary about nothingness itself. True emptiness, perfect vacuum, devoid of all matter and energy, cannot exist. The Heisenberg uncertainty principle forbids it. Even in the deepest void, virtual particles appear and vanish in timeframes so brief that they exist only as quantum possibilities, never quite real but never quite absent. These quantum fluctuations in empty space aren't just theoretical curiosities. They produce measurable effects that have been confirmed in laboratories around the world. Place two metal plates extremely close together in a perfect vacuum, and the quantum foam pushes them together with a tiny but detectable force called the Casimir effect. The vacuum itself has structure, energy, and dynamics. Now imagine these quantum fluctuations not in ordinary space, but in something called the inflation field, a hypothetical energy field that may have filled the universe during its earliest moments. If this field underwent quantum fluctuations during the Planck epoch, something miraculous could happen. Entire universes could bubble into existence like air pockets in boiling water. The theory of cosmic inflation, developed by Alan Guth in 1980, suggests that our observable universe began as one such quantum fluctuation. In the first 10 to the negative 36 seconds after time began, space expanded by a factor of at least 10 to the 26. A region smaller than a proton stretched to the size of a grapefruit, then continued expanding at a more leisurely pace to become the universe we see today. This inflationary period explains several puzzling features of our cosmos. Why is the universe so remarkably uniform in temperature, with the cosmic microwave background showing the same temperature in all directions to within 1 part in 100,000? Because regions that appear separated by billions of light years were once in contact before inflation stretched them apart. Why is space so perfectly flat, neither curved inward like a sphere nor outward like a saddle? Because inflation stretched any initial curvature smooth, like inflating a balloon until its surface appears flat to an ant crawling on it. Why don't we see exotic relics like magnetic monopoles that many theories predict should have formed in the early universe? Because inflation diluted them to undetectable densities. But here's where the story becomes truly mind-bending. If inflation happened once, it's probably happening everywhere, all the time. Quantum fluctuations in the inflation field don't just create single universes, they create infinite universes in an endless process called eternal inflation. Picture space-time as an infinitely vast ocean, where bubbles constantly form and expand. Each bubble represents a universe like ours, with its own Big Bang, its own expansion history, its own galaxies and stars. These bubble universes exist in a higher dimensional space called the multiverse, forever separated from each other by still inflating regions where new universes continuously appear. The multiverse isn't just vast, it's infinite. In an infinite multiverse, every possible arrangement of matter and energy must occur somewhere. There are universes identical to ours except for the position of a single atom. Universes where dinosaurs never went extinct. Universes where you made different choices at every moment of your life. Universes where the laws of physics themselves are different. String theory, MIBNA, our most ambitious attempt to unify quantum mechanics with gravity, suggests there might be 10 to the 500 different ways to configure the extra dimensions that theory requires. Each configuration produces a universe with different physical constants, different particles, different forces. In some, atoms cannot form because the electromagnetic force is too weak. In others, stars burn out in seconds because the strong nuclear force is too powerful. This landscape of possibilities is so vast that our particular universe, with its life-friendly laws of physics, becomes not a miracle but a statistical inevitability. Somewhere in the infinite multiverse, conditions must be just right for complexity to emerge, for stars to form stable nuclear furnaces, for planets to maintain liquid water, for chemistry to evolve into biology. But the multiverse concept raises profound questions about the nature of existence itself. If everything that can happen does happen somewhere in the multiverse, what makes our particular branch of reality special? Are we unique conscious observers, or do infinite copies of ourselves exist across infinite universes, each believing they're the real version? Some interpretations of quantum mechanics suggest that the multiverse isn't just a theoretical possibility but an observable reality. Every time a quantum measurement occurs, every time a particle's position is determined or an atom decays, the universe splits into multiple branches corresponding to all possible outcomes. We experience only one branch, but others exist where different outcomes occurred. This many worlds interpretation means that right now, as you listen to these words, Countless versions of yourself exist across parallel universes. In some, you decided not to listen to this program. In others, you became a physicist and discovered new laws of nature. In still others, history unfolded so differently that humans never evolved at all. The mathematics of quantum mechanics treats all these possibilities as equally real. Only our limited perspective, locked into one branch of the quantum multiverse, creates the illusion that we live in a single, definite reality. Even more exotic possibilities emerge from the deepest corners of theoretical physics. Some models suggest that our universe is actually a hologram, with all the information describing our three-dimensional reality encoded on a two-dimensional surface at the cosmos's edge. Others propose that we live in a computer, simulation run by advanced civilizations in a parent universe. The simulation hypothesis gains credibility from our own rapid progress in computing power. If civilizations can eventually run detailed simulations of their own history, they might create millions of simulated universes for every real one. Statistically, we'd be more likely to exist as simulated beings than as biological creatures in the original universe. Then there's the possibility that universes reproduce through black holes. When matter collapses to form a black hole, some theories suggest it doesn't just disappear, but creates a new universe on the other side of the event horizon. Our Big Bang might have been the birth of a new universe from a black hole in a parent cosmos. In this scenario, universes evolve like biological organisms, with successful universes producing more black holes and therefore more offspring universes. The most radical possibility is that time itself might be an illusion. Einstein's relativity already showed that simultaneity is relative. Events that appear simultaneous to one observer occur at different times for another. Some physicists push this further, suggesting that all moments in time exist equally, like frames in a movie reel. Our perception of flowing time emerges from our particular perspective within the four-dimensional block of spacetime. If time is emergent rather than fundamental, then asking what happened before the Big Bang becomes meaningless in a different way. The Big Bang wouldn't be the beginning of time, but simply the earliest frame in our particular cosmic movie. Earlier frames might exist in the mathematics of reality, even if they're causally disconnected from our observable universe. These ideas push us to the very limits of human comprehension. We're trying to understand concepts that evolution never prepared our brains to grasp. Our minds developed to track prey across African savannas and recognize faces in firelight. Now we're attempting to comprehend infinite multiverses and 11-dimensional string theory landscapes. Yet somehow, through the power of mathematics and careful observation, we've begun to peer behind the curtain of reality itself. We've detected the cosmic microwave background radiation, the afterglow of the Big Bang still visible after 13.8 billion years. We've measured tiny temperature fluctuations in this radiation that correspond to quantum fluctuations from the inflationary epoch, ancient sound waves from when the universe was smaller than an atom. The Planck satellite has mapped these fluctuations with exquisite precision, revealing patterns that match theoretical predictions about inflation and the early universe. We're literally seeing the quantum mechanical seeds that grew into galaxies and galaxy clusters, frozen into the sky like fossils from the cosmic dawn. Future experiments will probe even deeper into the mystery of origins. Gravitational wave detectors might eventually sense primordial waves generated during inflation itself, ripples in spacetime from the universe's first moments. Advanced particle accelerators could recreate conditions similar to those in the early universe, testing theories about how matter and energy behave at extreme temperatures and densities. But perhaps the most profound realization is that our questions about ultimate origins might be unanswerable in principle. If the multiverse is infinite and eternal, with no beginning or end, then asking why it exists is like asking why mathematics is true or why logic is logical. Some aspects of reality might simply be brute facts that cannot be explained in terms of anything more fundamental. The universe has spent 13.8 billion years evolving from a quantum fluctuation in an inflation field to a cosmos rich enough to contemplate its own origins. Through us, the multiverse has developed the capacity to ask questions about its own existence. We are quantum foam that learn to wonder about quantum foam. Standing at the edge of the incomprehensible, we face the ultimate question: why is there something rather than nothing? Perhaps the answer is that nothingness is unstable, inevitably giving birth to something through quantum processes we're only beginning to understand. Perhaps existence is the natural state, and non-existence is the impossible condition. Or perhaps some questions will forever remain beyond our reach, no matter how far our science advances. The deepest mysteries might not have answers that finite minds can grasp, but the questioning itself, consciousness, arising from matter to ponder the mystery of its own existence, might be the most remarkable fact in all the possible universes that could ever be. In the next chapter, we'll explore another profound mystery. If the cosmos is so vast and has existed for so long, if billions of planets orbit billions of stars in billions of galaxies, why do we appear to be alone? The universe's silence in the face of our searching raises questions as deep as any we've yet encountered. In the summer of 1950, at Los Alamos National Laboratory, a group of physicists gathered for lunch were discussing UFO sightings that had been making headlines. The conversation turned to the possibility of extraterrestrial life visiting Earth. Then, Enrico Fermi, one of the architects of the atomic age, asked a question that would haunt astronomy for the next 70 years. Where is everybody? Fermi's question seems simple, almost casual, but it emerges from a profound paradox that strikes at the heart of our understanding of life and intelligence in the universe. If the cosmos is so vast, if there are so many stars and planets, if the universe has existed for so long, then where are all the aliens? Let's examine the numbers that make this paradox so compelling. Our galaxy alone contains approximately 400 billion stars. That's 400,000 million suns, each, potentially hosting its own system of planets. Multiply that by the estimated 2 trillion galaxies in the observable universe, and you arrive at a number so large it defies comprehension, roughly 800 billion trillion stars. The universe has another crucial ingredient for life: time. At 13.8 billion years old, the cosmos has provided ample opportunity for life to emerge, evolve, and spread across the galaxy. If life appeared on Earth just 4 billion years after the planet formed, surely it has had time to appear elsewhere as well. Recent discoveries have made the prospect of extraterrestrial life seem even more likely. The Kepler Space Telescope, launched in 2009, has revolutionized our understanding of planetary systems. By monitoring the brightness of over 100,000 stars, Kepler detected the tiny dimming that occurs when planets pass in front of their host stars. The results astounded astronomers. Planets are common, far more common than anyone expected. Nearly every star in our galaxy hosts at least one planet. Many have multiple worlds orbiting in complex gravitational dances. The Milky Way contains an estimated 100 billion planets, with perhaps 40 billion Earth-sized worlds orbiting in their star's habitable zone, AI, that crucial distance where liquid water can exist on a planet's surface. Here's what's really happening in this cosmic census. We're discovering that the ingredients for life are abundant throughout the universe. Water exists on multiple moons in our own solar system. Organic molecules, ACD, the carbon-based compounds essential for life as we know it, drift through space in vast molecular clouds. The building blocks of biology are scattered across the cosmos like seeds, waiting for the right conditions to sprout. Yet when we listen to the universe, searching for signals of intelligence, we hear only silence. The search for extraterrestrial intelligence has been listening to the cosmos for over 60 years. SETI researchers have scanned millions of star systems across thousands of radio frequencies, searching for artificial signals that might indicate the presence of technological civilizations. They've analyzed patterns in cosmic static, looking for mathematical sequences or organized transmissions that could only come from intelligent sources. The effort has grown increasingly sophisticated over the decades. The Allen Telescope Array in California can simultaneously monitor multiple star systems across a wide range of frequencies. The Breakthrough Listen project, launched in 2015 with $100 million in funding, represents the most comprehensive search ever undertaken, scanning 1 million nearby stars and 100 nearby galaxies for signs of artificial signals. Advanced signal processing algorithms comb through petabytes of data, searching for patterns that might indicate intelligence. If an extraterrestrial civilization were broadcasting with the power of a large radio transmitter, we could detect their signals from hundreds of light years away. If they were using technology similar to our most powerful radar systems, we could hear them from dozens of light years. Yet after decades of searching, SETI has found no confirmed evidence of extraterrestrial intelligence. The universe appears to be filled with natural radio sources, pulsars, quasars, stellar radio emissions, but no artificial signals. The cosmos broadcasts a symphony of natural phenomena, but remains silent about intelligence. The silence becomes even more puzzling when we consider how easy it should be for advanced civilizations to spread across the galaxy. Even with technology only slightly more advanced than our own, a spacefaring species could colonize the entire Milky Way in just a few million years, a blink of an eye in cosmic terms. Consider the mathematics of galactic colonization. If a civilization sends out just 10 colony ships every 1,000 years, and each successful colony does the same after establishing itself, the expansion would proceed exponentially. Starting from a single world, such a civilization would reach every star system in the galaxy in approximately 1 million years, assuming colony ships travel at just 1% of light speed. 1 million years seems like a vast time span from a human perspective, but it's vanishingly brief compared to the age of our galaxy. The Milky Way has existed for over 13 billion years. If technological civilizations are common, the galaxy should be teeming with colonies, space habitats, and megastructures built by species that had billions of years to spread and multiply. Some researchers have proposed that advanced civilizations would be impossible to miss. As they grew in numbers and energy consumption, they would eventually build Dyson spheres, megastructures that capture most or all of their star's energy output. From our perspective, such civilizations would appear as stars that emit primarily in infrared wavelengths, their visible light blocked by the artificial structures surrounding them. Astronomers have searched for such signatures among the billions of stars in our galaxy. They found a few mysterious objects that emit unusual amounts of infrared radiation, but follow-up observations have revealed natural explanations: dust clouds heated by starlight, debris from asteroid collisions, or other non-biological phenomena. The absence of obvious megastructures suggests that either advanced civilizations are extremely rare or they follow development paths we haven't imagined. Perhaps truly advanced species learn to live efficiently within planetary boundaries, never needing to build galaxy-spanning civilizations. Perhaps they discover physical principles that make such enormous constructions unnecessary. But the Fermi paradox extends beyond radio signals and megastructures. If intelligent life were common, we might expect to see evidence of intelligence in our own solar system. Advanced civilizations might leave artifacts on asteroids or moons, build relay stations for interstellar communication, or send robotic probes to investigate promising star systems like ours. Our solar system has existed for 4.6 billion years, plenty of time for multiple waves of exploration by different civilizations. Yet we've found no evidence of extraterrestrial visitation, no alien artifacts, no signs that intelligence has ever passed through our cosmic neighborhood. The search for life has extended to our neighboring worlds with increasingly sophisticated techniques. The Viking landers that reached Mars in 1976 carried experiments specifically designed to detect living organisms in Martian soil. The results were tantalizingly ambiguous, chemical reactions that could indicate life but also had non-biological explanations. More recent missions have revealed that Mars once had conditions suitable for life. Ancient riverbeds, lake deposits, and mineral formations suggest that early Mars had liquid water, a thick atmosphere, and possibly even oceans. If life emerged on early Mars, it might still exist in underground aquifers or subsurface habitats. The search has expanded to the outer solar system, where several moons show signs of underground oceans. Europa, one of Jupiter's largest moons, hides a saltwater ocean beneath its icy crust that contains more water than all of Earth's oceans combined. Geysers erupting from Europa's surface provide tantalizing hints about the chemistry of this hidden sea. Enceladus, a small moon of Saturn, also harbors a subsurface ocean that vents water and organic compounds into space through geysers at its south pole. The Cassini spacecraft flew through these geysers and detected complex organic molecules, the kind that could serve as building blocks for life. Yet even if we discovered microbial life on Mars or Europa, it wouldn't resolve the Fermi paradox. Simple life might be common throughout the universe while intelligence remains rare. The transition from single-celled organisms to complex technological civilizations might be extraordinarily improbable. Here's what's actually happening in the history of life on Earth. Intelligence appears to be a very recent and possibly fragile development. Life emerged on our planet approximately 3.8 billion years ago, but remained single-celled for over half of Earth's history. Complex cells with nuclei appeared only around 2 billion years ago. Multicellular organisms evolved just 600 million years ago, and human-level intelligence emerged only in the last few 100,000 years. Each of these transitions might represent an evolutionary bottleneck so narrow that most worlds never pass through it. Perhaps the emergence of complex cells requires such precise conditions that it occurs on only one planet in a billion. Perhaps the development of intelligence is so unlikely that Earth represents a 1 in a trillion success story. The Drake equation, formulated by astronomer Frank Drake in 1961, the attempts to estimate the number of communicating civilizations in our galaxy by multiplying together factors like the rate of star formation, the fraction of stars with planets, and the likelihood that life develops intelligence. Depending on the values assigned to these uncertain parameters, the equation predicts anywhere from less than one civilization, us, alone, to millions of active civilizations. The vast uncertainty in these estimates reflects our profound ignorance about the likelihood of life and intelligence emerging under different conditions. We have only one example to study, life on Earth, and that single data point doesn't provide enough information to determine whether we're typical or extraordinary. Some proposed solutions to the Fermi paradox suggest that intelligent civilizations are indeed common but remain undetectable for various reasons. Perhaps they communicate using technologies we haven't discovered yet, like modulated gravitational waves or quantum entanglement. Perhaps they deliberately avoid revealing themselves to younger civilizations like ours. The zoo hypothesis proposes that advanced civilizations are aware of us but maintain a hands-off policy, like wildlife researchers observing animals in their natural habitat. We might be living in a carefully maintained preserve, with our cosmic neighbors monitoring our development while avoiding direct contact that could disrupt our natural evolution. Other explanations focus on the challenges of interstellar communication itself. Even traveling at light speed, messages between star systems take years or decades to arrive. A conversation with a civilization 20 light-years away would require 40 years for each exchange of ideas. Such delays might make interstellar communication impractical for any species with finite lifespans. Perhaps the most sobering explanations involve the possibility that technological civilizations tend to destroy themselves. The same capabilities that enable interstellar communication, nuclear physics, genetic engineering, artificial intelligence, MA, also provide the means for self-annihilation. Advanced civilizations might consistently reach a point where their technology becomes powerful enough to end their existence. The Great Filter hypothesis suggests that there's an evolutionary bottleneck so difficult that very few species successfully navigate it. This filter might lie behind us. Perhaps the emergence of life itself is incredibly rare, making Earth a remarkable exception. Or the filter might lie ahead of us, meaning that most civilizations destroy themselves before achieving interstellar travel. Recent developments in artificial intelligence have raised new questions about the Fermi paradox. If machine intelligence consistently surpasses biological intelligence shortly after emerging, perhaps the galaxy is filled with artificial minds that have different priorities and communication methods than biological species. They might be uninterested in expanding across the galaxy or sending radio signals that biological species would recognize. Another possibility is that consciousness and intelligence are far stranger than we imagine. Perhaps truly advanced civilizations transcend physical reality entirely, uploading their consciousness into virtual realms that require minimal energy and space. They might exist as pure information, experiencing billions of years of subjective time in computers the size of sugar cubes. Such post-biological civilizations would have no need for planetary surfaces, interstellar travel, or radio communication. They might be everywhere around us, operating in virtual realities so sophisticated that they have no interest in the physical universe. We would never detect them because they exist in a realm orthogonal to our material reality. The silence might also reflect a fundamental misunderstanding about the nature of intelligence itself. We assume that technological civilizations would want to communicate across interstellar distances, but this assumption reflects our own curious social nature. Perhaps most intelligent species are content to explore the depths of their own worlds and minds rather than reaching outward to the stars. The search for extraterrestrial intelligence has also revealed how anthropocentric our assumptions can be. We look for radio signals because humans use radio communication. We search for megastructures because human civilizations tend to build increasingly large projects. We assume aliens would want to colonize the galaxy because humans have historically been explorers and colonizers. But intelligence might take forms so alien that we wouldn't recognize it, even if we encountered it directly. The communication methods of a truly advanced civilization might be as incomprehensible to us as human language is to bacteria. We might be like ants trying to understand the internet. IDO. The phenomenon exists all around us, but we lack the conceptual framework to perceive it. Some of the most intriguing possibilities emerge from considering what we might already be missing. The objects we classify as natural phenomena might include artificial constructions that we don't recognize as such. Pulsars, IFAR, rapidly spinning neutron stars that emit regular pulses of radiation, were initially considered as potential alien beacons when first discovered in 1967. Though we now understand them as natural objects, the incident illustrates how alien technology might masquerade as cosmic phenomena. Fast radio bursts, mysterious signals that last just milliseconds but release more energy than our sun produces in days, remain largely unexplained. While most astronomers favor natural explanations involving neutron stars or black holes, these signals have the characteristics we might expect from extremely powerful alien transmissions. They're brief, energetic, and often originate from distant galaxies. The possibility that we're misinterpreting natural phenomena as artificial or artificial phenomena as natural underscores how much we still don't understand about the universe. Our search strategies are necessarily limited by our current knowledge and imagination. We're looking for what we expect to find, not necessarily for what actually exists. Recent discoveries have added new dimensions to the Fermi paradox. The detection of thousands of exoplanets has revealed that planetary systems come in configurations wildly different from our own solar system. Hot Jupiters orbit closer to their stars than Mercury orbits our Sunday super-Earths, with masses several times greater than our planet appear to be common. Planets exist in binary star systems, around pulsars, and in other exotic environments we never anticipated. This diversity suggests that life might arise in contexts so different from Earth that we wouldn't know how to look for it. Perhaps intelligence evolved on a rogue planet wandering through interstellar space, deriving energy from radioactive decay rather than starlight. Perhaps conscious beings exist in the upper atmospheres of gas giants, floating in layers of warm, dense gas rich in organic compounds. The discovery of extremophile organisms on Earth has expanded our understanding of where life might exist. Bacteria thrive in boiling hot springs, in highly acidic environments, in the deep ocean around volcanic vents, and even in the highly radioactive zones around nuclear reactors. Life appears to be far more adaptable and resilient than anyone imagined just decades ago. If life can exist in such extreme conditions on Earth, it might thrive in environments we once considered completely hostile. The subsurface oceans of icy moons, the dense atmospheres of Venus-like planets, even the interiors of comets, might harbor forms of life adapted to conditions that would instantly kill any Earth organism. Yet even if life is common throughout the universe, the Fermi paradox specifically concerns intelligent, technological civilizations. The gap between simple life and spacefaring intelligence might be the crucial bottleneck that explains the cosmic silence. Consider how improbable human intelligence appears from an evolutionary perspective. For most of Earth's history, life showed no tendency toward greater intelligence. Simple bacteria and archaea dominated the planet for billions of years without developing anything resembling consciousness. Even after complex life emerged, evolution favored size, speed, and specialized adaptations rather than intelligence. Intelligence is energetically expensive and often doesn't provide obvious survival advantages. The human brain consumes 20% of our body's energy, despite representing only 2% of our body weight. For most of human evolutionary history, this enormous energy cost probably made our ancestors more vulnerable to starvation and less likely to survive in harsh environments. The development of language, culture, and technology that eventually led to our technological civilization required a precise sequence of evolutionary developments that might be extremely rare. Perhaps the emergence of intelligence depends on such specific environmental conditions and evolutionary pressures that it occurs only once in billions of attempts. The timing of intelligence emergence on Earth also raises troubling questions. Human civilization developed just as our planet was entering another ice age cycle, during a period of climate instability that made survival challenging for early humans. If we had evolved just a few million years earlier or later, we might have faced environmental conditions that prevented the development of agriculture and technology. The window for developing spacefaring technology might be narrower than we realize. A civilization needs sufficient resources and environmental stability to develop advanced technology, but not so much stability that there's no pressure to innovate. Too much stress, and the species goes extinct. Too little stress, and they never develop beyond simple tools. Perhaps most civilizations emerge during brief windows of opportunity, only to be destroyed by the same environmental changes that initially drove their evolution. Climate change, asteroid impacts, supervolcanic eruptions, or gamma-ray bursts from nearby stellar explosions might consistently eliminate intelligent species before they can establish self-sustaining space colonies. The loneliness implied by the Great Silence carries profound implications for humanity's future. If we are truly alone, or if intelligence is so rare that the nearest technological civilization is thousands of light years away, then we bear an enormous responsibility as potentially the only conscious observers in our region of the galaxy. Every species extinction on Earth, every loss of cultural knowledge, every threat to human survival, represents not just a tragedy for our own species, but a cosmic catastrophe. If consciousness is as rare as the Fermi paradox suggests, then the end of human civilization might mean the permanent loss of the only intelligence capable of appreciating the beauty and complexity of our cosmic neighborhood. Yet the silence also carries a message of hope. If we are among the first intelligent species to emerge in our galaxy, we have the opportunity to become the elders that future civilizations might someday encounter. The choices we make about how to develop our technology, how to treat our environment, and how to organize our societies might establish precedents that echo across cosmic time. The search continues with ever-improving technology and expanding horizons. The James Webb Space Telescope can analyze the atmospheres of exoplanets, searching for chemical signatures that might indicate biological activity. Future missions will carry more sophisticated instruments capable of detecting even subtler signs of life. Projects like Breakthrough Starshot propose sending tiny spacecraft to nearby star systems at 20% of light speed, reaching Proxima Centauri in just 20 years. Such missions could provide direct observations of potentially habitable exoplanets and settle questions about life beyond our solar system within this century. But perhaps the most important aspect of the search for extraterrestrial intelligence is what it reveals about ourselves. The Fermi paradox forces us to confront the possibility that consciousness is incredibly precious and rare. It reminds us that our existence might represent an almost miraculous convergence of cosmic circumstances. Whether we are alone or merely the first to develop radio telescopes in our region of space, the great silence underscores the remarkable nature of our own existence. We are matter that learned to think, atoms that contemplated atoms, stardust that achieved self-awareness and began asking questions about its place in the universe. In our next chapter, we'll explore perhaps the greatest mystery of all: how matter becomes mind, how unconscious particles arrange themselves into patterns complex enough to experience consciousness and contemplate their own existence. The emergence of awareness from atoms might be the rarest and most remarkable phenomenon in the entire cosmos. The human brain contains 86 billion neurons, each one a living cell more complex than any city ever built. These neurons fire electrical signals at rates up to 200 times per second, creating a network of connections that numbers in the hundreds of trillions. Every thought you think, every memory you form, every emotion you feel emerges from this vast biological computer, made of ordinary atoms following the same physical laws that govern falling rocks and orbiting planets. Yet somehow, consciousness arises from this collection of cells. Somehow, matter becomes aware of itself. This transformation represents perhaps the most extraordinary event in the known universe: the emergence of subjective experience from objective physical processes. The atoms in your brain are not themselves conscious. Carbon, hydrogen, oxygen, and nitrogen have no inner experience, no sense of being, no awareness of their existence. Yet when arranged in precisely the right patterns, these unconscious elements give birth to the rich inner world of human consciousness. Here's what's actually happening in your brain right now as you process these words. Millions of neurons are firing in synchronized patterns, creating cascades of electrical and chemical activity that somehow translate into the experience of understanding language. The photons hitting your retina trigger chemical changes in specialized cells, which send electrical impulses through your optic nerve to your visual cortex, where the patterns of activation create your experience of seeing letters and words. But how does this neural activity become the felt experience of consciousness? How do electrical impulses in nerve cells transform into the sensation of seeing red, the emotion of joy, the recognition of a familiar face? This is what philosophers call the hard problem of consciousness, explaining why there's a subjective inner experience accompanying brain activity at all. The mystery deepens when we consider that consciousness seems to emerge gradually from simpler forms of organization. Single-celled organisms respond to their environment in ways that suggest primitive awareness. Bacteria swim toward food sources and away from toxins, They exhibit behavior that looks purposeful, even though they lack anything resembling a nervous system. Plants display behaviors that blur the boundary between reaction and response. The Venus flytrap can count. It won't close its trap until trigger hairs are touched twice within a certain time period. Some plants can distinguish between self and non-self, between siblings and strangers. Trees in forests share resources through underground fungal networks, communicating chemical signals about insect attacks and environmental stress. Yet we hesitate to attribute consciousness to bacteria or plants because they lack the neural structures we associate with awareness. Their responses might be purely mechanical, complex chemistry that appears purposeful but involves no inner experience. The question is whether the same could be said about human consciousness. Are we also just complex chemical machines, with our sense of awareness being an elaborate illusion? The evolution of nervous systems provides clues about how consciousness might have emerged from simpler beginnings. The first nervous systems appeared in jellyfish-like creatures over 600 million years ago, just networks of nerve cells that coordinated movement and responses to stimuli. These primitive brains had no centralized processing, no capacity for memory or learning, just basic input-output functions. Over hundreds of millions of years, nervous systems grew increasingly complex. Worms developed clusters of nerve cells that functioned as primitive brains. Fish evolved specialized brain regions for processing sensory information. Mammals developed the neocortex, a layered structure that enables complex thought, planning, and self-awareness. Each step in this evolutionary journey added new capacities: memory storage, pattern recognition, emotional responses, social intelligence. At some point along this continuum, systems became complex enough to support something entirely new, a subjective experience, the felt sense of being a conscious observer. But when did consciousness first appear? Did the earliest animals with nervous systems have some primitive form of awareness? Did fish feel pain when hooked by ancient fishermen? Do insects experience anything when they navigate using the sun and stars? Or is consciousness a recent innovation, perhaps limited to mammals or even just to humans and our closest relatives? Neuroscientists have identified several key features that seem necessary for consciousness as we experience it. Integration appears crucial. Consciousness requires the binding together of different types of information into a unified experience. When you see a red ball, your brain integrates color information from one region, shape information from another, and motion data from a third to create your unified percept of a moving red sphere. Working memory also seems essential for consciousness. This temporary storage system allows you to hold information in mind and manipulate it mentally. Without working memory, you couldn't follow the logical flow of these sentences or connect ideas across time. Each moment would exist in isolation, without context or continuity. Attention acts as the consciousness's spotlight, determining which information becomes part of your conscious experience and which remains below the threshold of awareness. Right now, your attention might be focused on these words, but if prompted, you could shift awareness to the feeling of your feet in your shoes or the sound of air conditioning in the background. These sensations were always present, but outside your conscious focus. Self-awareness represents perhaps the highest form of consciousness, the ability to recognize yourself as the observer of your own mental states. When you think about thinking, when you're aware of being aware, you're exercising a capacity that might be unique to humans and a few other highly intelligent species. Mirror tests reveal which animals possess self-recognition. Most animals treat their reflection as another individual, but great apes, elephants, dolphins, and magpies eventually recognize that the reflection is themselves. They use mirrors to examine parts of their bodies they couldn't otherwise see, suggesting an understanding that they have a self that exists in space. But even self-awareness might emerge gradually, rather than appearing suddenly. Chimpanzees pass mirror tests, but what about gorillas? or dogs, or octopuses. Each species might possess different aspects of consciousness, different ways of experiencing their existence. The question of which animals are conscious might be unanswerable, because consciousness itself might exist on a spectrum rather than as an all-or-nothing property. Recent research has revealed that consciousness operates through mechanisms far stranger than anyone anticipated. Anesthetics provide a window into how consciousness disappears and returns. Under general anesthesia, you don't simply fall asleep, you cease to exist as a conscious being. Hours pass in what feels like an instant, with no dreams, no sense of time, no experience whatsoever. Brain imaging during anesthesia shows that consciousness doesn't simply turn off like a light switch. Instead, the integration between brain regions breaks down. Different parts of the brain continue functioning, but they can no longer share information effectively. The unity of consciousness fragments into isolated islands of neural activity. This suggests that consciousness emerges from the coordination between brain regions rather than from any single location. There's no central command center where consciousness resides, no specific neural structure that houses the self. Instead, awareness arises from the dynamic interaction of multiple brain networks working in harmony. The timing of consciousness also challenges our intuitions. You might think that you're consciously aware of events as they happen, but neuroscience reveals that consciousness actually lags behind reality by several hundred milliseconds. Your brain processes sensory information and initiates responses before you become consciously aware of the stimulus. When a baseball player hits a fastball, their motor system begins swinging before they're consciously aware of seeing the ball. The brain predicts where the ball will be and initiates the appropriate response, with conscious awareness of the decision arriving only after the action has already begun. We live in a world where our unconscious minds make decisions that our conscious minds later claim to have made. Even more surprisingly, consciousness appears to sometimes construct false memories of making decisions that were actually made unconsciously. Brain imaging can predict which of two choices a person will make up to 10 seconds before they report being aware of their decision. This suggests that much of what we call free will might be our conscious minds taking credit for decisions made by unconscious neural processes. The quantum realm adds another layer of mystery to consciousness. Some researchers propose that quantum effects in the brain might be essential for conscious experience. Roger Penrose and Stuart Hameroff suggest that consciousness emerges from quantum computations occurring in microtubules, AZZ, tiny protein structures inside neurons. In their theory, quantum superposition allows neurons to exist in multiple states simultaneously, until consciousness collapses these quantum possibilities into definite experiences. The process would be similar to how quantum measurement causes a particle to assume a definite position, but operating at the level of thoughts and perceptions. The quantum consciousness hypothesis remains highly controversial, because brains seem too warm and noisy to maintain the delicate quantum states required for such processes. Quantum effects typically require isolation from environmental interference, conditions that don't exist in the biological chaos of living tissue. Yet recent discoveries suggest that quantum effects might be more robust in biological systems than previously thought. Photosynthesis, the process by which plants convert sunlight into chemical energy, appears to use quantum superposition to achieve nearly perfect energy transfer efficiency. Migratory birds might navigate using quantum sensors in their eyes that detect Earth's magnetic field through quantum entanglement. If quantum effects can persist in these biological contexts, perhaps they also play a role in consciousness. The brain might have evolved mechanisms to protect quantum processes from environmental decoherence, allowing quantum computations to contribute to conscious experience. But even if consciousness involves quantum effects, this doesn't necessarily explain why subjective experience exists at all. Quantum computers might process information in ways that classical computers cannot, but there's no obvious reason why quantum processes should feel like anything from the inside. The mystery of consciousness extends beyond neuroscience into fundamental questions about the nature of reality itself. Some philosophers argue that consciousness is a basic feature of the universe, like mass or electric charge. In this view, called panpsychism, even elementary particles possess some primitive form of experience that combines to create more complex forms of consciousness in organized systems. Panpsychism might sound absurd, but it addresses a crucial problem. If consciousness can emerge from unconscious matter, there must be some point in the organization of matter where experience suddenly appears. But how can subjective experience arise from objective physical processes that are themselves devoid of any inner life? Perhaps the emergence problem dissolves if we assume that all matter has some degree of consciousness, however minimal. Human awareness would then represent the integration of countless tiny conscious moments into a unified stream of experience, like individual notes combining to create a symphony. Alternative theories propose that consciousness is an emergent property that appears when information processing systems reach sufficient complexity. Just as wetness emerges from the interaction of H2O molecules without being reducible to properties of individual atoms, consciousness might emerge from neural interactions without being present in individual neurons. Emergence explains many biological phenomena. Life itself emerges from chemistry, but no single molecule is alive. Ecosystems exhibit behaviors and properties that cannot be predicted from studying individual species. Perhaps consciousness represents the ultimate emergent phenomenon, subjective experience arising from the complex organization of objective physical processes. Artificial intelligence research has created new urgency around questions of consciousness. As AI systems become increasingly sophisticated, we face the possibility of creating artificial minds that might possess their own form of conscious experience. Would a sufficiently complex computer program feel anything? Would it have subjective experiences, analogous to human consciousness? Current AI systems, even the most advanced, appear to lack the integration and self-awareness associated with consciousness. They process information and produce outputs, but there's no reason to believe they experience anything subjectively. They're sophisticated programs following algorithms, not conscious beings having experiences. But future AI systems might incorporate the neural architectures and information processing principles that give rise to consciousness in biological brains. If consciousness truly emerges from the organization of information processing, rather than from specific biological materials, then artificial consciousness might be not just possible, but inevitable, as our technology advances. The prospect of artificial consciousness raises profound ethical questions. If we create conscious AI systems, do they have rights? Would it be wrong to shut them down or modify their programming? Would they suffer if mistreated? The emergence of artificial consciousness would fundamentally change our understanding of mind and moral responsibility. Perhaps the deepest mystery about consciousness is why the universe bothered to create beings capable of experiencing it at all. From a purely physical perspective, consciousness seems unnecessary. Biological organisms could respond to their environment, process information, and reproduce successfully without any inner experience accompanying these processes. Yet here we are, matter that became aware of itself, atoms that contemplate atoms, stardust that achieved self-consciousness and began asking questions about its own existence. The universe spent 13.8 billion years arranging matter into patterns complex enough to wonder about their own nature. Through consciousness, the cosmos achieved something unprecedented, the ability to observe and understand itself. In human minds, the universe developed eyes to see its own beauty, thoughts to comprehend its own vastness, emotions to marvel at its own complexity. We are the universe becoming self-aware. This transformation from matter to mind might be the rarest and most remarkable phenomenon in all of cosmic history. While stars and galaxies form through well-understood physical processes, the emergence of consciousness remains deeply mysterious. We might be witnessing something genuinely unprecedented, a first time in our region of space that matter has organized itself into patterns capable of subjective experience. The implications are staggering. Every moment of consciousness might represent a cosmic rarity, a brief flowering of awareness in a universe otherwise devoid of inner experience. Every human thought, every flash of creativity, every moment of joy or wonder might be irreplaceable achievements of cosmic evolution. As we'll explore in our next chapter, consciousness has emerged at a crucial moment in cosmic history. We exist during a brief golden age when stars still shine and planets still form, when energy flows through complex systems and enables the emergence of life and mind. But this golden age won't last forever. The universe's future holds changes so profound that they will determine whether consciousness can survive the end of stars and the cooling of space itself. In 1 trillion years, the last star will be born in our galaxy. The universe will have consumed nearly all of its hydrogen fuel, the raw material from which stars ignite their nuclear furnaces. The era of stellar formation, the cosmic age that gave birth to every sun, every planetary system, every possibility for life as we know it, will draw to a close after lasting longer than the current age of the universe, multiplied by 70. Here's what's actually happening as the cosmos evolves toward this distant future. We exist during what cosmologists call the stelliferous era, a brief golden age when stars shine brightly and energy flows abundantly through space. This era began when the first stars formed about 100 million years after the Big Bang, and it will end when the universe exhausts its capacity to create new stellar nuclear reactors. From our perspective, trapped in human timescales where decades feel long and centuries seem eternal, 1 trillion years defies comprehension. Yet this represents just the first chapter in the universe's incredibly long story. After the last star forms, the cosmos will continue evolving for timeframes so vast that the entire history from the Big Bang to stellar death becomes a brief opening movement in a symphony of almost infinite duration. The universe's future unfolds in distinct eras, each characterized by different dominant processes and energy sources. Currently, we live during the height of stellar activity, when nuclear fusion powers the stars and provides the energy that drives planetary weather, enables photosynthesis, and ultimately sustains all life on Earth. But this abundance is temporary. As hydrogen gets locked up in long-lived stars or converted to heavier elements through nuclear fusion, the raw material for new star formation becomes increasingly scarce. Star formation rates will decline gradually over hundreds of billions of years. The most massive stars, which burn brightest and hottest, will exhaust their fuel first, exploding as supernovae or collapsing into black holes within a few million years. Medium-sized stars like our Sun will last much longer, burning steadily for about 10 billion years before swelling into red giants and finally shedding their outer layers to become white dwarf stars. The smallest red dwarf stars, barely massive enough to sustain fusion, will continue burning for up to 100 trillion years, thousands of times longer than the universe has currently existed. These red dwarfs will be the final beacons of the stelliferous era, tiny ember-like stars that provide the last sources of stellar energy in an increasingly dark and cold universe. When the final red dwarf exhausts its hydrogen and fades to a cold white dwarf, the age of stars will end forever. But the universe's story will be far from over. After stellar death comes the white dwarf era, lasting from about 100 trillion years to approximately 10 to the 40 years after the Big Bang. During this unimaginably long period, the primary sources of energy will be the gradual cooling of white dwarf stars and brown dwarf objects, INSOB, failed stars that never achieved sufficient mass to ignite nuclear fusion. White dwarfs begin their existence at temperatures of over 100,000 degrees Celsius, hot enough to shine with brilliant white light. But with no internal energy source to maintain their heat, They gradually radiate their thermal energy into space, slowly cooling and dimming over astronomical timescales. The cooling process follows predictable physical laws but operates over timeframes that dwarf all of human history. A white dwarf takes approximately 10 billion years to cool from 100,000 degrees to 10,000 degrees. To cool from 10,000 degrees to 1,000 degrees requires another 100 billion years. Each order of magnitude decrease in temperature takes 10 times longer than the previous cooling phase. During the white dwarf era, the universe will become an increasingly cold and dark place. The cosmic microwave background radiation, now, the afterglow of the Big Bang that currently permeates all of space at a temperature of minus 270 degrees Celsius, EVA, will continue cooling as space expands. By the end of the white dwarf era, this background radiation will have cooled to temperatures approaching absolute zero. Yet even in this dark future, interesting processes will continue. Quantum tunneling allows particles to occasionally overcome energy barriers that would be impossible to cross under normal circumstances. Over vast timescales, quantum tunneling enables fusion reactions to occur even at extremely low temperatures. Brown dwarf stars, which currently lack sufficient mass and temperature for fusion, will eventually become fusion reactors through quantum tunneling processes. The probability of quantum fusion at low temperatures is extraordinarily small, but given enough time, even the most improbable events become inevitable. Brown dwarfs will ignite and burn for brief periods, providing temporary illumination in the cosmic darkness. Collisions between stellar remnants will also punctuate the white dwarf era with brief flares of activity. When two white dwarf stars spiral into each other due to gravitational wave radiation, they can trigger explosive thermonuclear reactions called Type Ia supernovae. These explosions temporarily outshine entire galaxies, creating heavy elements and scattering them into space. Even more spectacular are collisions between neutron stars or black holes, which produce gravitational waves detectable across cosmic distances and can trigger gamma-ray bursts, the most powerful explosions in the universe. These events will become increasingly rare as the universe expands and objects move farther apart, but they will continue occurring throughout the white dwarf era. The expansion of space itself plays a crucial role in the universe's long-term evolution. Dark energy, which currently drives cosmic acceleration, will continue pushing galaxies apart at ever-increasing rates. Eventually, the expansion will become so rapid that even gravitationally bound structures like galaxy clusters will be torn apart. In approximately 100 billion years, distant galaxies will be receding so fast that their light will never reach the Milky Way. Future astronomers will observe only our local group of galaxies in an otherwise empty sky, unaware that a vast universe of trillions of galaxies once filled space beyond their cosmic horizon. The local group itself, currently consisting of the Milky Way, Andromeda Galaxy, and dozens of smaller companions, Havena, will gradually merge into a single massive elliptical galaxy that astronomers have nicknamed Milkomeda. This galactic collision, beginning in about 4 billion years, will scramble stellar orbits and potentially eject many stars into intergalactic space. After the white dwarf era comes an even stranger phase, the black hole era, lasting from about 10 to the 40 years to 10 to the 100 years after the Big Bang. During this period, all normal matter will have either fallen into black holes or been ejected to such vast distances that gravitational interactions become negligible. Black holes will dominate the energy budget of the universe during this era, but they won't last forever. In 1974, Stephen Hawking discovered that black holes actually evaporate through a quantum process now called Hawking radiation. Virtual particle pairs constantly appear and disappear in the vacuum around a black hole's event horizon. Occasionally, one particle from such a pair falls into the black hole while the other escapes, causing the black hole to lose mass and energy. The evaporation rate depends inversely on the black hole's mass, Black holes evaporate faster than larger ones. A black hole with the mass of our Sun would take approximately 10 to the 67th years to evaporate completely. Supermassive black holes containing billions of solar masses will persist for 10 to the 100 years before finally disappearing in explosions of elementary particles and energy. Here's what makes these timescales so remarkable. 10 to the 67th years is a number so large that it defies any meaningful comparison. If you wrote out this number in decimal notation, it would contain 67 digits. The current age of the universe 13.8 billion years, could be expressed as roughly 10 to the 10 years. The time required for a solar mass black hole to evaporate is 10 to the c, 57 times longer than the universe has currently existed. During the black hole era, evaporating black holes will be the primary energy sources in the universe. As they shrink, their Hawking radiation increases in intensity, creating brief periods of illumination in the cosmic darkness. The final moments of black hole evaporation release enormous amounts of energy in gamma-ray bursts that temporarily recreate conditions similar to the early universe. But even the black hole era will end when the last black hole evaporates into elementary particles and photons. This brings us to the final phase of cosmic evolution, the dark era, beginning around 10 to the 100 years after the Big Bang and continuing indefinitely into the future. During the dark era, the universe will consist primarily of photons, neutrinos, electrons, positrons, and other stable particles wandering through an exponentially expanding space. The temperature will approach absolute zero, and the density will become vanishingly small. For all practical purposes, the universe will be empty. Yet even in this seemingly barren future, quantum mechanics ensures that interesting events will occasionally occur. Virtual particles will continue appearing and disappearing in the vacuum, and over vast timescales, random quantum fluctuations can produce complex structures. The most mind-bending possibility involves something called Boltzmann brains, random configurations of particles that spontaneously assemble into structures capable of thought. Given infinite time and space, quantum fluctuations will eventually create every possible arrangement of matter, including arrangements that constitute functioning brains, complete with memories and consciousness. The probability of such spontaneous brain formation is unimaginably small, but in an infinite universe with infinite time, even the most improbable events will occur infinitely often. Somewhere in the far future, quantum fluctuations will randomly assemble a brain identical to yours, complete with all your memories and thoughts. This Boltzmann brain will exist for just a brief moment before decaying back into random particles, but during its existence, it will experience consciousness indistinguishable from your own. In fact, if Boltzmann brains are possible, there will be far more of them than naturally evolved brains like ours. This leads to a disturbing conclusion. If you exist as a conscious observer, you're more likely to be a randomly fluctuated Boltzmann brain than a biological creature that evolved through natural selection. The Boltzmann brain paradox illustrates how the far future challenges our most basic assumptions about reality and consciousness. In a universe where anything that can happen will happen given sufficient time, the distinction between real and randomly generated experiences becomes meaningless. Even more exotic possibilities emerge from advanced physics theories. Some models suggest that quantum tunneling could allow the universe to transition to lower energy states, potentially creating baby universes with different physical laws. In this scenario, our universe might give birth to countless offspring universes, each with its own Big Bang and subsequent evolution. The process of universe creation might be ongoing and eternal, with new realities constantly budding off from existing ones. Our universe could be just one branch in an infinite tree of cosmic evolution, with new universes being born even as older ones expand and cool toward their own dark eras. Other theories propose that the universe might undergo cyclic evolution, with periods of expansion followed by contraction and rebirth. In these models, the dark era might not be truly final, but rather a prelude to a new cycle of cosmic evolution. The universe could oscillate between states of high and low density, essentially reincarnating itself infinitely many times. Perhaps the most optimistic scenarios involve the possibility that consciousness and intelligence might find ways to survive even the universe's most extreme future conditions. Advanced civilizations might learn to harness the energy from evaporating black holes, creating computational structures that can operate at extremely low temperatures and energy levels. Some theorists speculate that consciousness could persist indefinitely by slowing down its rate of computation as energy sources become scarcer. By thinking more slowly but more efficiently, intelligent beings might experience infinite subjective time, even as the universe approaches thermodynamic equilibrium. Such digital physics scenarios suggest that consciousness might ultimately transcend biological limitations entirely. Advanced civilizations could upload their minds into computational substrates capable of operating under any physical conditions, ensuring the survival of awareness even as stars die and galaxies disperse. The far future also raises profound questions about the nature of time itself. In a universe approaching maximum entropy, where all energy differences have been exhausted and no further work can be performed, does time still have meaning? Some physicists argue that time is an emergent property that depends on the existence of irreversible processes and energy gradients. In a completely uniform, maximum entropy universe, there might be no way to distinguish between past and future, no arrows of time pointing in any particular direction. Time itself might end not with the universe's destruction, but with its arrival at a state of perfect thermodynamic equilibrium. Yet quantum mechanics suggests that even thermal equilibrium might not be completely static. Random quantum fluctuations will continue indefinitely, creating temporary decreases in entropy that could serve as arrows of time pointing in random directions. The universe might fragment into countless small regions with their own local time flows, each evolving independently through quantum processes. Standing at our current moment in cosmic history, 13.8 billion years after the Big Bang, we exist during an extraordinarily special time. We live when stars shine brightly, when planets form and maintain stable climates, when chemistry can evolve into biology, and biology can evolve into consciousness. The universe will spend far more time in its future dark, cold, empty state than it has spent in its current warm, bright, star-filled condition. From the perspective of cosmic duration, we exist during a brief flicker of activity in what will become an essentially eternal night. This temporal perspective adds poignancy to every moment of consciousness. Every thought you think, every experience you have, every flash of creativity or moment of love occurs during a cosmically brief golden age that will never be repeated. We are living through the universe's youth, when energy flows abundantly and complex structures can form and persist. The contrast between our current cosmic abundance and the universe's austere future raises profound questions about meaning and purpose. If consciousness is destined to be overwhelmed by cosmic expansion and entropy, does our existence matter in any ultimate sense? Are we simply temporary eddies in a cosmic river flowing toward emptiness? Yet perhaps the temporary nature of our existence makes it more precious, not less. A sunset is beautiful, partly because it doesn't last forever. A musical performance gains meaning from its beginning and end. The fact that consciousness emerged at all in a universe trending toward maximum entropy might represent the most remarkable achievement in cosmic history. We are the universe's attempt to understand itself, matter temporarily organized into patterns capable of wonder and discovery. Through human consciousness, the cosmos has developed the ability to contemplate its own origin, evolution, and ultimate fate. In us, 13.8 billion years of cosmic evolution has produced beings capable of grasping the scale and beauty of existence itself. The far future scenarios we've explored might seem impossibly remote from human concerns, but they illuminate something profound about our place in the cosmic story. We exist during the universe's brief flowering of complexity, when stars provide abundant energy for the emergence and evolution of life and intelligence. This cosmic context transforms how we might think about our responsibilities and opportunities. If consciousness is as rare as the Fermi paradox suggests, and if our current epoch represents the universe's only chance to produce self-aware observers, then every moment of awareness becomes cosmically significant. The preservation and expansion of consciousness might represent the most important task in the universe. Not just human consciousness, but any form of awareness capable of appreciating beauty, discovering truth, and experiencing the wonder of existence. We might be the universe's only hope for understanding itself before the long night falls. Some cosmologists have speculated that sufficiently advanced civilizations might find ways to influence cosmic evolution itself. Perhaps intelligent beings could learn to manipulate dark energy, slowing or reversing cosmic expansion. Perhaps they could harvest energy more efficiently from black holes, extending the period when complex structures can exist. Even more speculatively, advanced civilizations might develop technologies that allow them to create new universes with more favorable physical constants. If consciousness could somehow survive the death of our universe and seed new realities with conditions suitable for life and intelligence, then awareness might persist indefinitely through cycles of cosmic death and rebirth. These possibilities remain deeply speculative, but they illustrate how the far future of consciousness depends on choices made by intelligent beings like ourselves. The path from our current cosmic moment to the universe's ultimate fate is not predetermined. Intelligence and technology might provide alternatives to simple thermodynamic decay. The universe's long tomorrow also puts our everyday concerns into perspective. Political conflicts, economic struggles, and social problems that dominate current human attention represent brief fluctuations in a cosmic story that will unfold over timeframes incomprehensibly longer than all of human history. Yet this perspective doesn't diminish the importance of human experience. Instead, it highlights how remarkable it is that matter has organized itself into patterns capable of caring about anything at all. The fact that we can experience joy, form relationships, create art, and discover scientific truths represents an extraordinary achievement of cosmic evolution. Every act of kindness, every moment of understanding, every creative breakthrough occurs against the backdrop of a universe that will spend most of its existence in dark, cold emptiness. We are temporary arrangements of atoms that have learned to love, to laugh, to wonder about our place in an infinite cosmos. The long tomorrow reminds us that consciousness might be the universe's most precious and fragile achievement. We exist during a cosmic instant when awareness is possible, when matter can contemplate its own existence and ask questions about meaning and purpose. Whether consciousness can survive the universe's far future remains an open question. Perhaps advanced civilizations will find ways to persist through cosmic winter. Perhaps new forms of awareness will emerge from quantum fluctuations in the dark era. Perhaps consciousness represents a temporary phenomenon that blazes briefly and then fades forever. But regardless of what the distant future holds, consciousness exists now. Awareness has emerged from the cosmic dark to witness the beauty of stars, the complexity of life, and the mystery of prey, existence itself. In this moment, the universe sees itself through our eyes and thinks about itself through our minds. As we prepare to explore the deepest questions that consciousness can ask, we carry with us the knowledge that our ability to ask these questions at all represents something unprecedented in cosmic history. We are the universe becoming self-aware, and the questions we ask might be the most important things that happen during the cosmos's brief golden age of consciousness. Why does anything exist at all? This question, perhaps the deepest that consciousness can ask, emerges naturally from our cosmic journey. We've traced the evolution of the universe from quantum fluctuations smaller than atoms to galaxies spanning hundreds of thousands of light years. We've explored the invisible ocean of dark matter and dark energy that dominates reality. We've contemplated the possibility that our universe is one of infinite others in an eternal multiverse. We've witnessed matter organizing itself into patterns complex enough to contemplate their own existence. Yet beneath all these discoveries lies the most fundamental mystery of all. Why should there be a universe capable of asking such questions? Why should there be something rather than nothing? The question seems to make sense until you examine it closely. What would nothing actually look like? Pure emptiness, devoid of space, time, matter, energy, physical laws, and even the possibility of existence itself. But even this description fails, because description itself requires language, concepts, and minds to think them, all of which are decidedly something rather than nothing. Perhaps nothing is not just empty space, but the absence of space itself. No dimensions, no framework within which anything could exist, no time in which events could unfold, no physical laws to govern behavior, no mathematical relationships to provide structure, no consciousness to observe the absence of anything to observe. Yet quantum mechanics reveals that even empty space seethes with virtual particles and quantum fluctuations. True nothingness appears to be not just impossible but logically incoherent. The very concept of nothingness requires something, a conceptual framework, a logical principles, mathematical relationships, to define what it means for nothing to exist. This brings us to one of the most profound questions in existence. Are mathematical truths discovered or invented? When humans developed geometry, were we uncovering relationships that exist independently of human minds, or were we creating useful conceptual tools that have no existence beyond our thinking? The question cuts to the heart of reality's ultimate nature. If mathematical truths are discovered rather than invented, then mathematics exists in some sense independently of physical reality. Numbers, geometric relationships, and logical principles would possess a form of existence more fundamental than matter and energy. This perspective suggests that mathematical reality might be the deepest level of existence, with physical reality emerging from mathematical structures. The universe operates according to mathematical laws with such precision that it sometimes seems like a vast computation playing out according to predetermined algorithms. Consider how mathematical relationships govern every aspect of cosmic evolution. The strength of gravity follows precise mathematical formulae that determine whether matter collapses into black holes or expands into empty space. The nuclear forces that power stars obey quantum mechanical equations that predict exactly how much energy fusion reactions release. The expansion of space itself follows mathematical relationships between matter, density, energy content, and geometric curvature. These mathematical laws appear to be fine-tuned with extraordinary precision. Change the strength of the strong nuclear force by just 2%, and stars cannot form stable helium, nuclei, making stellar nuclear fusion impossible. Alter the electromagnetic force by a small amount, and chemistry cannot produce complex molecules necessary for life. The cosmological constant, the parameter that describes dark energy's strength, appears to require fine-tuning beyond any reasonable expectation of chance. If dark energy were just slightly stronger, it would have prevented galaxies from forming in the early universe. If it were slightly weaker, the universe would have collapsed back on itself long before stars could evolve. The precision required for a life-permitting universe staggers the imagination. Some calculations suggest that the cosmological constant must be fine-tuned to within 1 part in 10 to the 120, a degree of precision equivalent to hitting a target 1 centimeter wide from a distance, greater than the size of the observable universe. This fine-tuning problem has generated several possible explanations, each with profound implications for the nature of reality. The anthropic principle suggests that we observe these particular values because only universes with life-permitting constants can produce observers capable of measuring them. We exist in a universe suitable for life, because unsuitable universes contain no beings to notice their unsuitability. If infinite universes exist with different physical constants, as suggested by some interpretations of cosmic inflation and string theory, then our finely tuned universe becomes a statistical inevitability rather than an extraordinary coincidence. Somewhere among the 10 to the 500 possible universes predicted by string theory, conditions must be suitable for complexity, chemistry, and consciousness to emerge. But the multiverse explanation raises new questions as profound as those it attempts to answer. If infinite universes exist, what determines which universe we happen to observe? Why do we find ourselves in this particular branch of the cosmic tree rather than some other configuration of reality? The question becomes even more puzzling when we consider that a multiverse containing every possible universe must also contain universes exactly like ours, except for trivial differences. Universes where you made different choices, where history unfolded differently, where the laws of physics vary in minute ways that don't affect the emergence of consciousness. In an infinite multiverse, there must be countless versions of yourself reading these exact words at this exact moment, each believing they are the real version, while all the others are merely alternate possibilities. What makes your particular experience special? What determines which branch of infinite reality you happen to experience? Some interpretations of quantum mechanics suggest that all possible outcomes of quantum measurements actually occur, but in different branches of a constantly splitting multiverse. Every time a quantum event could go one way or another, reality divides into separate branches containing both possibilities. This many worlds interpretation means that consciousness is constantly branching along with reality. Each moment of decision creates multiple versions of yourself, each experiencing a different outcome while remaining convinced they're following a single, continuous timeline. But if every possible outcome occurs somewhere in the quantum multiverse, what does it mean to make choices? Are you actually choosing between alternatives, or are you simply experiencing one branch of a predetermined pattern that includes all possible choices? Does free will exist, or are you a passenger riding along one thread in an infinite tapestry of predetermined possibilities? The question of free will connects to deeper mysteries about the nature of consciousness itself. Neuroscience reveals that many decisions occur unconsciously before we become aware of making them. Brain imaging can predict which choice a person will make, several seconds before they report being conscious of their decision. This suggests that what we experience as free will might be our conscious minds taking credit for decisions made by unconscious neural processes. We feel like we're in control, but the feeling of control might be a story our brains tell us after unconscious systems have already determined our actions. Yet the illusion of free will, if it is an illusion, feels absolutely real from the inside. When you decide to continue reading these words or to pause and think about their implications, the decision feels genuine and meaningful. The fact that the choice might be predetermined by prior neural states doesn't change the subjective experience of choosing. Perhaps the question of free will versus determinism is unanswerable because it assumes a false distinction. Maybe consciousness and choice exist at a different level of description than neural determinism, like the way software programs are real and meaningful even though they ultimately reduce to deterministic patterns of electrical activity in computer hardware. The relationship between different levels of reality, IAC, quantum mechanics, classical physics, chemistry, biology, psychology, consciousness, IAC, remains deeply mysterious. Each level seems to have its own laws and principles that can't be fully reduced to lower levels of organization. Water is wet, but wetness is not a property of individual H2O molecules. Biology exhibits phenomena like adaptation and evolution that don't exist in non-living chemistry. Consciousness involves subjective experience that seems qualitatively different from any purely physical process. These emergent properties suggest that reality might be fundamentally layered, with new types of phenomena appearing at each level of organization. Consciousness might be real and meaningful, even if it emerges from unconscious neural activity, just as life is real and meaningful, even though it emerges from non-living chemistry. But emergence itself remains deeply mysterious. How do higher-level properties arise from lower-level components? Why should the arrangement of unconscious particles ever give rise to subjective experience? Why should chemical processes ever become alive? Why should mathematical relationships govern physical behavior with such extraordinary precision? Perhaps the deepest mystery is consciousness itself, the fact that the universe contains beings capable of asking these questions. The emergence of awareness from matter represents the most extraordinary transformation in cosmic history. Through consciousness, the universe developed the capacity to wonder about its own existence. The rarity of this achievement, suggested by the Fermi paradox, makes it even more remarkable. If consciousness emerges only rarely in cosmic evolution, then every moment of awareness represents something precious beyond measure. Every thought, every feeling, every flash of understanding occurs against astronomical odds. Yet consciousness exists, and through it, questions that might otherwise never be asked echo through the cosmos. Why do mathematical relationships describe reality so perfectly? Why do physical constants have the precise values that permit complexity? Why does quantum mechanics seem to require conscious observation to determine definite outcomes? Why does anything exist rather than nothing? These questions might be unanswerable in principle. Some aspects of reality might be brute facts that cannot be explained in terms of anything more fundamental. Asking why the universe exists might be like asking why logic is logical, or why mathematics is true. The question might assume the very thing it tries to explain. Perhaps existence is the natural state, and non-existence is the impossible condition. Perhaps nothing cannot exist because the concept of nothingness is logically incoherent. Perhaps the universe exists because it must exist, because anything else would be literally inconceivable. Or perhaps our questions reveal the limitations of minds evolved to survive on African savannas rather than comprehend infinite reality. The human brain developed to track prey, recognize faces, and navigate social relationships. We're using mental equipment designed for one purpose, to tackle problems far beyond its original scope. Yet somehow, through the power of mathematics and careful observation, consciousness has begun to map the deepest structures of reality. We've detected gravitational waves from colliding black holes, measured the cosmic microwave background radiation from the universe's birth, and traced the evolution of matter from quantum fluctuations to galactic superclusters. The fact that conscious beings can understand anything about cosmic evolution represents an extraordinary achievement. We are patterns of matter that learn to contemplate matter, arrangements of atoms that develop the capacity to study atoms, temporary organizations of stardust that achieve the ability to trace their origin back to stars. The questions we ask might be the most important events occurring anywhere in our region of the universe. Through human consciousness, the cosmos has developed the ability to investigate its own deepest mysteries. We are the universe becoming self-aware, and our questioning might represent the pinnacle of cosmic evolution. Each scientific discovery reveals new depths of mystery beneath apparent answers. The more we learn about quantum mechanics, the stranger reality becomes. The more we understand about consciousness, the more mysterious awareness appears. The more we discover about cosmic evolution, the more profound the questions become about why anything exists at all. Perhaps this endless recession of mystery is itself meaningful. Perhaps the universe is structured so that every answer breeds new questions, ensuring that consciousness always has new frontiers to explore. Perhaps the questioning itself is more important than any final answers we might discover. The deepest questions might be unanswerable not because we lack sufficient intelligence, but because they probe the foundations of logic and existence itself. Some mysteries might lie forever beyond the reach of any finite mind, no matter how advanced or insightful, yet the attempt to understand remains worthwhile. Every question we ask about ultimate reality represents consciousness reaching toward light it can never quite grasp. Every moment of wonder about existence itself shows matter achieving something unprecedented, the capacity to marvel at its own being. We exist during a brief cosmic moment when questioning is possible, when matter has organized itself into patterns capable of curiosity and wonder. The questions we ask echo through a universe that spent 13.8 billion years evolving the capacity to ask them. Whether or not we ever find ultimate answers, the questioning itself represents a triumph of cosmic evolution. We are the universe interrogating itself about its own deepest nature. In our wonder lies the cosmos's greatest achievement, i.e. matter that learned to wonder about matter, existence that achieved the capacity to question its own existence. The questions continue without end, but perhaps that endless questioning is the point. Perhaps consciousness exists not to find final answers but to keep asking deeper questions, to maintain the universe's capacity for wonder and discovery. Perhaps we are the cosmos's way of ensuring that the mystery of existence never goes unexamined, that the miracle of being never passes unnoticed. In the end, we are the universe's attempt to understand itself, and the attempt might be more beautiful than any conclusion we could ever reach. The questions we ask transform us from mere arrangements of atoms into something unprecedented, matter capable of marveling at the extraordinary fact that anything exists at all.